Hello, everyone. My name is Ranga Narayanan. I'm a professor in chemical engineering at the University of Florida. My short presentation will have to do with fluid physics for material science and space. I'm going to specifically focus on one aspect, an important aspect of fluid physics called resonance, and I'll show to you how I believe fluid resonance can be used profitably to benefit material science and space. There are many applications of fluid physics that principally involve space habitation, life support that includes water, food, thermal control, and air revitalization. Also, problems that involve radiation shielding, dust mitigation, and protection from the environment. All of these, in principle, will involve the use of materials. These materials can be obtained from in situ resource utilization, from using regolith, or by reusing tools. Now, to use these resources, the principal ways by which we will be able to put these resources to use is by additive manufacturing and by materials processing. In both of these processing methods or techniques, we will need to have a good understanding of fluid physics. Now, the science concepts and technology that will be tested can use platforms that involve just ground-based testing, or where we could use length scales that effectively diminish the effect of gravity. We can use small microgravity time platforms such as parabolic flights, or intermediate microgravity time platforms that include recoverable satellites, or long duration microgravity time platforms such as the International Space Station. In all of these, we should always remember that the quality of the microgravity, including G-jitter and understanding of the background noise, is important as we go through various science objectives, no matter what the materials processing methods are, or no matter what the fluid physics are. Now, the low gravity platforms typically involve parabolic flights. Here is an image of a jet executing a parabolic maneuver through Zero-G Corporation. The typical microgravity time is between 12 to 18 seconds. There are also intermediate microgravity time platforms, such as those being offered by Blue Origin. Here you may get a few minutes of microgravity time. And of course, there is the International Space Station, where there is a substantial amount of microgravity time and equipment and other facilities on board. So we'll talk about at least a couple of these and some of the projects that we have. And I'll also try to raise some of the scientific questions that these projects have brought into the open. Now, we might ask, where does fluid physics play a role in additive manufacturing? So when we think of additive manufacturing, typically what comes to mind is 3D printing. Here is I'll try to move this aside, is a 3D printer from Ciali Corporation. And this is a depiction of a wire made of the metal or metallic alloy, which comes out of a feeder. It is heated by means of an electron beam to form a puddle. And on the left, you can see a movie or a depiction of this puddle being formed. Now, as the puddle is being formed, a substrate at the bottom moves back and forth, and this liquid metallic alloy creates a layered deposit that solidifies. An important thing to remember is that you do not wish to have any ripples being formed on this puddle, because these ripples will create a signature on the solidified tool or object and can compromise the mechanical structure of such an object. The formation of ripples can be minimized by optimizing the motion of the platform. The optimal condition is given by a dimensionless group called the Weber number, which is the ratio of the kinetic energy of the motion of the platform to the surface energy of the liquid metal in contact with the ambient atmosphere, such as, which might be typically nitrogen or argon, for example. This means that we need to have an accurate knowledge of surface tension and other properties, in fact, which will come into play, such as density, viscosity, and thermal conductivity. The reason we need to have accurate knowledge of these thermophysical properties is that if we were to do this sort of 3D printing in space, we must understand that the power and the energy requirements for doing this 3D printing comes at a cost, and there's a premium on this because there are other uses for this energy. So in order to make sure that we make avail of the energy in the most optimum way, we've got to have the optimum operating conditions for this sort of manufacturing process. And such optimum conditions mean that we should have accurate knowledge of these thermophysical properties that can then get coded into the machine so that we can make the objects with the least amount of effort. One of the important things, therefore, is the measurement of thermophysical properties. And we would like to know what are the what creative ways can we employ to measure these thermophysical properties. One such method is by using resonance. Now, I'll try to explain what I mean by this here. On the left, I have an animation, and on the right, I have a depiction of a furnace. So what we have in this animation is a metal that is suspended between two electrodes, one at the bottom, one at the top. And once it's suspended by employing an electrostatic field, it's heated in situ by means of a laser. And as soon as it gets heated and it's molten, provided it's a small mass of metal and also ultimately a small volume, we can create a spherical drop. This spherical drop will move like a solid, will move like a rigid body up and down if the electrodes are subject to an alternating field. Now, if you keep increasing the frequency of this alternating field, then this rigid body motion of the sphere will change, the sphere will undulate, and you will get a certain mode. This mode will cause the sphere, or will cause the drop, which was once a sphere, to undulate from prolate to oblate structures. Now, on the right, you've got a depiction of a solid suspended or effectively levitated between two electrodes. It will be heated by means of a laser and subject to this alternating field. If the frequency is large enough, this sphere of liquid will then ultimately undulate as seen in the movie on the left and seen in the depiction on the left. The frequency at which it begins to undulate is called the resonant frequency. This means that the frequency of the imposed alternating field is commensurate with the natural frequency of the sphere. This resonant frequency, when matched with the natural frequency, causes this sphere to go into all manners of modes, the lowest mode being shown here. And that natural frequency correlates directly to the surface tension. So what we have here is, on the left, an actual image taken from experiments done at NASA Marshall Space Flight Center of a zirconium droplet at 1800 degrees C. And you can see that at about 185 degrees Celsius, this droplet goes into these excited modes, whereas less than 185, the excursion is very small, and greater than 185, as shown to the right, let's say about 191, the excursion is also very small. So there's really this optimum frequency at which the excursions are very large. Having noted this frequency, which is now the natural frequency, we introduced this into a formula derived by Lord Rayleigh. And you can see from this formula that the frequency squared is related to a number of quantities. The first is the surface tension given by gamma. It's also related inversely to the density of the liquid metal and the radius of the sphere when this drop was once a sphere. So from this natural frequency, we can determine the surface tension once you know the mode into which it excites. That you can see visually. This mode, which you're seeing on the left, corresponds to a bimode, and that corresponds to this integer in the numerator of this formula, n, little n, equal to 2. So little n equal to 2 implies it goes from prolate to oblate. Now, you can get all manners of modes, which we can now depict in this movie at the bottom, where we now have water droplets. These were experiments done at JAXA in Japan, where water droplets were excited in a small lab levitator to go from frequency n equal to 2 to 3 to 4. The important thing to note is that if you do decide to use liquid metals on a ground levitator and want to measure the surface tension, inevitably you'll have to have the atmosphere as vacuum. Because if you try to levitate a very heavy metal, say in argon or say nitrogen, very typically the DC voltage needed to levitate the solid and ultimately to create a liquid from it is so large that very often short-circuiting or arcing will take place. So one way to get away from this is to try to do the levitation in space, where you do not need very great amount of forcing to levitate the solid and to make it into a sphere. You can also have larger radii of drops in space, which is somewhat difficult on ground because large radius spheres tend to sag and you really don't get a sphere at all. So an advantage to go to space is that you can use different ambient fluids such as nitrogen and argon. A second advantage is that you can use larger radius drops and go through a sweep of frequencies. Now, this experiment will be run on the International Space Station in the Japanese side of the International Space Station called Kibo, where there is an excellent facility, the electrostatic levitation furnace facility called ELF, depicted here. And you can see two astronauts, Tim Capra and Scott Kelly, floating in front of the ELF in Kibo. We expect to run our experiments with several materials to test our theories of getting resonant frequencies of different modes and being able to compare those values with what we get on ground. Now, there are other ways to measure key thermophysical properties that do not necessarily involve levitation. One such way is to take the liquid metal and put it on a conductive dish as shown here and place the dish on top of a bottom electrode. Then apply an alternating voltage across the surface of that liquid metal. And what you'll see is are a series of patterns, which I've now shown here. These patterns occur at specific frequencies, different frequencies, and these patterns and their frequencies can be correlated to the surface tension. Now, an interesting thing is that an alternating electrostatic voltage selectively reduces the effect of gravity. Now, it will not completely eliminate gravity. It will reduce the effect of gravity, bringing out the effect of surface tension. If you wish to bring out the effect of surface tension even more, you can take this experiment on a short duration microgravity flight, such as on a parabolic mission. And this is a project that we have proposed and which we will be running on a parabolic flight, where we will be comparing our measured frequencies and patterns and make that comparison with results that we will get on ground. It is our expectation that from this, a technology can evolve wherein we can get very accurate measurements of surface tension without necessarily levitating, yet also measure not only surface tension between liquids and vapor, or liquids and gases, but also interfacial tension between two liquids, because that is also important for other forms of material processing, such as crystal growth. Now, there are many science and technology questions that come out from the research that I've just talked about, and some of it have to do with this. Can we use multiple frequencies on levitated drops to excite multiple modes? And if we do so, can we learn anything and get anything practical out of this? Can we perhaps measure viscosity and even shear modulus of viscoelastic materials, not only when we use electrostatic resonance, but perhaps when we use mechanical resonance by, say, shaking a fluid mechanically, or by imposing acoustic resonance, by imposing acoustic signals. And this means that we can get more data, not just surface tension, viscosity, perhaps even shear modulus. Can we employ resonance to eliminate convection? Now, this is a new idea, because resonance not only makes a stable system unstable, but it will make an erstwhile unstable system, say a thermoconvective system, stable. So if you take a convective system and you try to shake it, you will actually begin to stabilize it. In other words, you have a system which is causing convection on Earth due to thermal gradients, due to buoyancy, or in space due to Marangoni convection. Perhaps by imposing acoustic signals or mechanical resonance or even electrostatic resonance, we can quench that convection. So in summary, I'd like to point out that fluid physics, particularly that of resonance, can be potentially used to solve key technological problems in space. These include the measurement of key thermophysical properties for optimal additive manufacturing and materials processing, such as crystal growth, and maybe even reducing or eliminating undesirable flows during materials processing. I hope that some of the science that I've introduced and some of the scientific questions that I've raised will give rise to interesting conversations. Thank you very much.